In this class, we're going to consider how you differentiate composite functions using a technique called the chain rule. Once you've learned the power rule, which tends to be the first rule you learn in differentiation, usually you'll learn the chain rule pretty quickly afterwards. The power rule is good for polynomials, but only for kind of polynomial functions. So you need to start to learn how to differentiate other types of function. And the next level up is probably going to be either a trig function, which we look at in another class, or the functions we'll look at today, which you can use the chain rule on. The first thing is recognizing when you can use the chain rule. Technically it is for, like I said, composite functions. Remember, a composite function is one which is in the form h of x equals sum f of g of x. In other words, it's two functions kind of merged together, like composed, stuck together. If you're not familiar with composite functions, that's probably not a showstopper for taking this class, because the functions that we're going to differentiate, like these examples here, they don't really look anything like this. This is like the generic form of a composite function, but we're looking at a more specific example of a composite function. So that's really what the chain rule allows you to do. We're going to look at the mechanics of it in a second. So although it is to do with composite functions, don't worry too much about that. Just try and recognize some of the formats that are composite functions, and then you can use the chain rule. A typical scenario, although there are many, would be a bracket with a power. And you might look at that and think, well, how does that tally up with that? Well, basically there are two functions going on here. You've got this internal function, like the one inside the bracket, 2x minus 3, so that would be a polynomial function. And then you've got this kind of outer exponential function where you've got a bracket with a power on it. So you could define your g of x as being 2x plus 3, and then your f function as being like x to the power of 4. And then you're kind of merging those together, you're forming the composite. So that's why things that are in this format, like bracket with a power, are effectively polynomials and exponential functions merged together. When you come to differentiate these, you're going to probably end up seeing so many of these, you're not going to think exponentials and polynomials merged. You're just going to say, yeah, that's like, I need to use the chain rule for that. So you'll just go ahead and use the chain rule. There are other formats. So for example, you might see a trig function written something like, say, sine cubed x, which means the sine of x all cubed. Because it means the sine of x all cubed, that actually could be written in a bracket with a power. That now puts it in the form of a composite function. The internal function is sine x. You've got this exponential cubed function, so that would also be a scenario in which you would need to use the chain rule. We're not going to focus on those so much. It's still the same technique. We're going to focus on these more common methods here. There is, I guess, a formula for using the chain rule for these types. We're not going to talk about the formula as such. We're going to try and use a more intuitive, I guess, method. There's also a different way you can use you can do this using what's called a u substitution. So for this first one here, you would say something like let u equal 2x plus 3. I'm not going to use that method here. I think it's far too complicated, but I'm just saying that in case this is the method you've already learnt. It's absolutely fine, it works. It's maybe the method you might even see in a textbook, but a little bit overkill, I think, for that one. So we're just going to jump into a method which is kind of aligned with the power rule. So I'm focusing on how you're actually going to use the chain rule in practice. So we're just going to go straight to our derivative. There's no intermediate lines of work in here. All you do is you imagine that this is a power rule type question, in the sense that you've got something here with a power, and we're just going to take the power rule, use the power rule on that. So we would multiply by the power, imagining basically the bracket to be like a giant x term or something like that, as though this is like x to the power of 4. So you multiply by the power, you reduce the power by 1. So at that point we've just used the chain rule. The thing that then makes it, the power rule, the thing that makes it the chain rule is that we then multiply by the derivative of the inside of the bracket. The derivative of 2x plus 3 is 2, and it's that step on the end, that times them by the inside, that makes it the chain rule. You can take another line to merge these, because 2 times 4 will be obviously 8, just to tidy up the algebra. So it's kind of the power rule twice in a way. That's maybe one way to think about it. So just looking at another example, so go straight to the derivative here by multiplying by the power, which is minus 2. We're going to leave the bracket alone, so the bracket never changes. Take 1 off the power, so that goes down to a minus 3. And then we're just going to make that into the chain rule by timesing by the derivative. Derivative of the inside is 3. Take another line to merge these guys together to give you negative 6. 3x minus 5 to the minus 3. So I mentioned earlier you can use a kind of formulaic approach to this. The problem with the formulaic approach, notice that the derivative here came out to be 3, which was just this number here. The derivative here was 2, which is that number there. The formulaic approach tends to assume that the inside part of your bracket will always be in the form ax plus b, but as the next example shows, the inside of your bracket could be anything. It could be a far more complex polynomial than ax plus b, so that formulaic method is a little bit suspect. We don't like that. It can break down at some point. So applying our much cooler method to this one, obviously, we're going to differentiate using the power rule first. So multiplying by the power on the whole bracket, reducing the power by 1 to take that down to a 3, then pulling in the part that makes it the chain rule, which is now to differentiate the inside. Unlike these where we just got this number as the internal derivative, the derivative of this we need to use the power rule for. 3 times 2 is 6, reduce the power by 1, and we're going to get 6x squared. So we've ended up with a more complex term there outside the bracket. Taking the same approach to merge these together, we're going to get 24x squared, 2x cubed minus 4 to the power of 3. So it's a little bit uglier, that one. But that's not untypical of the types of function you will have to differentiate using the chain rule. Okay, finally, let's take a look at this one. So first of all, we've got a y function, so we're going to have to differentiate using the notation dy dx. Just the same method again, so even though the polynomial is kind of spun around, doesn't really change the method. So multiply by the power, reduce the power by 1. I'm just going to write in the 1 there for illustration, but generally we don't write in the 1. But just for illustration, I've reduced that 2 down to 1. Now we're going to times that by the derivative of the inside. This guy's been spun around because the coefficient of the x is negative. So it just means that we're taking the derivative of this guy here, which is minus 3. So nothing really different there. It was just a different internal polynomial function. And then just tidying that up by multiplying these together. So minus 6 bracket 1 minus 3x, and then we'll just drop the 1 to leave it like that. So there are different routes into the chain rule, but the key points are to know that it's used technically for composite functions, but generally that's going to mean a bracket with a power on it. Not always. There are other types. As you get more experience with this topic and you see more questions, you might see variations on this. You'll just learn by experience when to use it. In terms of actually using it, try not to overthink it. It's just a power rule used twice, effectively. I find that that's the most helpful way to think about it. And it is a little tricky at first. As the examples get different, you'll just need to work a few practice questions until you're comfortable and know what to do in every different situation.